Okay, here we'll be going over the normal force with an inclined plane. This was quite tricky for me because I tried to figure it out myself, and I'm glad I could finally do so. I mean, it was just simple triangles. So here's what we're going to do. We're going to draw an inclined plane. And the reason why inclined planes are slightly more difficult to deal with is because we get to normal forces and gravity. And this is where gravity, which is technically only a downwards force, can be translated into an x force or a horizontal force, must you say. So let's say a box is resting up here. So let's recap our definitions of the normal force. But before we do so, remember um, gravity is only a downwards force, which is mass times acceleration, which you can convert to mass times gravity because gravity would be the accelerating force here. So let's say this is 15 degrees. This probably looks a little bit more like 45, but we'll just say 15. So a normal force is the force exerted straight perpendicular down from a surface. So here this would be it because this would be 90 degrees and 90 degrees. So let's do the mathematical proof here. If this is 15, then this is 90. And that would mean that a triangle has to have 180 degrees, meaning this would be 75 degrees, meaning this would be 15 degrees. And it becomes a new triangle. So whenever you have an inclined plane, I'm trying to draw the same inclined plane. Okay, there we go. This triangle with the box resting above it can be redrawn as a vector of this with the same angle measure being right here, this being 90 and this being the complement, or not the complement, but 90 minus the angle measure. And this allows us to use trigonometry to figure out the x and y components, or not the x and y components necessarily, because the y component would just be gravity, but it would allow us to find the normal force. So remember, this is straight downwards, so it'd be mass times acceleration, and we could simply use trigonometry. So sine 15 would be this, which would be the force that is parallel to, remember, the inclined plane, which goes this way, with the box on top of it. So if I had to redraw it here, just for reference, 15, sorry, it wouldn't be that, it'd be this, MA 15. This is parallel to this, which basically means that if we were to rotate this into a straight line, and it would look something like this, 15, and gravity is acting slightly a little to the left here, but that means that gravity would make the box slightly slide a little bit to the left here, because of the inclined plane, and this force would technically be the horizontal force here. So sine 15, and we'll denote this as, since this is force, we'll just say fx, or f parallel, I guess. The reason I'm using fx is because it looks like the x-axis, so sine 15 equals fx over mg, so fx equals mg sine 15, and fy is equal to mg cosine 15, but it's not even fy, it would be fn, which is the normal force. And remember, you multiply by that static or kinetic coefficient friction force to get how much force how much friction force is needed to overcome to turn into kinetic friction force, which is just mu k. But you don't need to know this is all you have to do. So to go over it quickly one more time, I'm going to draw this line. I'm gonna draw this line right there. And if a box is sitting on an inclined parallel thing, and this is x, then that means the parallel angle would also be x, and then use trigonometry. Remember, this is mg. The normal force is straight down, so it would be right here, which is written as Fn. And remember, the normal force is a force acting straight down on a perpendicular object. And then this would be f parallel. I wrote fx, but because if you make this straight, then it would look something like this, with the thing acting that way. And it would be, and the mass times gravity will be converted to a sideways force because of the inclined plane, which is pretty cool because now we can manipulate gravity to move, which is actually what I'm going to be doing for my second lab of my school year. So yeah, that's pretty scientific and genius. So yeah.